Awesome. All right. I think we'll start Savvas and give you as much time as possible to get through those slides. Everyone. Yeah. Awesome. Well, thanks everyone for joining us for this month's installment of the Cinema Community Science Seminar. We had a great presentation last month by Sarah Gasparini. If you're interested in viewing that, or if you missed it, it's available on our YouTube website channel. This week, we're really excited to have Dr. Savvas Raptis present to us. Savvas is a researcher here at APL and has done a lot of work recently with codes and MMS and geotail data looking at the storm time plasma sheet. It's been extremely helpful to us as part of kind of planning the parcel instrument along with some other works with people in this room. So we're really excited to have him on to present to the team and to the rest of the community on that work. So without further ado, Savvas, I'll let you take the screen and go for it.
Thank you, Adam, and thank you for giving me the chance to present this work. I'm sorry I couldn't be there, and I hope my internet connection is good enough. If there is any issue, just let me know. I'll try to move closer to the to the right. So let's begin. I will present you some of the findings we have in the last couple of years. The work is predominantly made through the CGS NASA Drive Center program that I acknowledge at the bottom. And just to give some context and synergy between this project, the CGS project, and cinema, one of the Center for Geospace Storm objectives is to understand the role of mesoscale plasma sheet transport in the ring current buildup. In order to understand this, we need to have a clear point of view on what happens to the plasma sheet, both during quiet conditions and during storm times. And of course, also understand how the global convection patterns are and the mesoscale ones in order to see the relative effect. And this brings us to cinema, where the actual overarching goal of cinema is to understand the role of plasma sheet structure and evolution in Earth's multiscale magnetospheric convection cycle. So there's a lot of synergy between those projects, and I'm really hoping that cinema will be able to answer a lot of the questions we still struggle with the data we have today. So the outline of the presentation I made basically consists of three different things. The first one is a relatively old work now. It's been more than a couple of years that I will briefly present on the global convection patterns regarding magnetic flux transport. Then we'll focus on bursty intervals, what we call BBFs or depolarization fronts and so on, and what are their properties and what asymmetries can be found in the magnetotail plasma sheet. And then I'll also show a machine learning model we've been working for quite a while. I did promise to myself that I would not present this until I submit it, so I hope that this is the last time I do this before this work is actually submitted in the near future. But basically what I will show is different data analysis that we have done with geotail and MMS, plus some Themis observations from the magnetotail plasma. So two of the things that I want to introduce before we go to the actual results that are very relevant to our work is the dawn-side current wedge. Dawn-side current wedge can be thought of as storm time phenomenon similar to the substorm current wedge. It is associated with an increased westward roll electrojet at the dawn sector. Here you can see some simulation results from Sarathi et al., where during the main phase of a storm, as you go towards higher difference between the partial ring current indices in the top panel, you also see the presence of depolarization and burst bulk flows happening at the dawn. A relatively similar, not similar, a connected phenomenon to this has to do with where magnetotail reconnection is being found. Here you can see from Nagai et al. 2023, the survey from geotail data, where they noted that while magnetotail reconnection is found mostly in the pre-midnight sector during typical activity, when we have strong solar wind driver, such as, for example, during storms, there seems to be a shift towards the dawn where reconnection mostly occurs. So with those two things in mind, how do we do any analysis of storm time when it comes to the magnetotail? I'll skip the first step because it's by far the most boring one, and I will go directly to the second, which is how to associate those data with different storms and different phases of those storms. So going directly to this step, the first thing we had to do was basically develop a storm finder and classifier in order to see when our data is during a main phase of a storm, a recovery phase, or during quiet time. So this, and I have another slide on that, is a very easy to maintain list. I already made it available online, and I've tried to update it regularly. I just realized that 2026 is not there, but I'll try to do that in the near future for anybody who wants to pick the list up and do any kind of analysis. And just a recent update regarding this list and other lists is that basically our list is what I call semi-automatic. In practice, it just uses a SciPy function that finds peaks and then has some parameters to tune it based on a complicated storm, which we use the Halloran storm as a good example. And then it has, I would say, 2% manual changes. Those were handmade just to make sure that there is no weird thing missing. For example, you can see here that this part in the Halloran storm was captured as a recovery phase. One could argue that maybe this part over here could have been a main phase classification. So things like that are very hard to catch. But you can see if you compare it with the top panel, which is a purely reproducible algorithm, that we do a pretty good job. And there was a paper published this week, actually, on Monday, that discusses how the different definitions of a storm can affect the storm list and what are the best practices for that. I already skimmed through it. I think it's a very, very interesting work. So I think everybody should take a look at it. So with those things in mind, the next step after we have the storm list is to understand where we are in the magnetotail. Here, many people have used different criteria to classify the plasma sets. In our example, we typically just assume that we want to be within 10 Earth radii in the YGSM coordinate. Beta should be significantly high, and there should be a magnetic inclination. This is just to make sure we are not in the sheath or the lobes. And after we do that, we end up with a relatively clean data set of both geotail and MMS data that we're going to discuss. You can see with the black the quiet time observations, with the blue the recovery, and red the main phase. This is the same color coding as before and remains the same throughout the presentation. Just some quick notes on that. As expected, geotail has been up in space for a longer time before it got down 2022, so it has many more data points. MMS doesn't have as many. This data set is up until 2024, so we have a few more since then. But still, because it was during solar minimum, the first period of time, we don't have that many storms, and therefore our statistics are relatively limited there. Just again, an extra note here. This is just the Venn diagram on the left on how the different criterion that people can use result in a data set. This is just to illustrate that classifying the plasma set and determining where we are sounds ridiculously easy when we say it out loud, but in practice it's not. And depending on the criteria you use, you can very easily skew your statistics or generate a sample that, especially during storm time, may not be representative of the conditions we look. I'll try to briefly talk about that later, but the key point here is just that it's always nice to check with different combinations of criteria and threshold whether the statistics we obtain are kind of always the same or not. So with this intro, I will start showing the results of our work. The first thing we did with the geotail data was to try and see what are the differences when in terms of convection. So we looked at EY and equivalently at the perpendicular to the magnetic field earthward velocity and BZ component. And what we found was that basically throughout the whole magnetotail, which you can see the distance in the x-axis, the convection electric field is elevated. And this elevation is shown more in the main phase of the storm, and it is attributed mostly to the elevated magnetic field that you can see on the panel C, and less to the elevation of velocity, which is slightly higher during storm time, but not significantly compared to the magnetic field. Now, if we move from this one-dimensional picture to a two-dimensional one, I plot this 2D histogram, which is kind of shows the difference between the same three quantities with respect to quiet time. So the x-axis shows again the x-GSM coordinate, the y-axis shows the y-GSM coordinate separating dusk and dawn, and each color bar indicates a different quantity. Essentially, the first one showing the difference in EY, the difference in perpendicular velocity with respect to the magnetic field towards the Earth, and BZ. And immediately you can see we have two different regimes, roughly speaking. The first one at the dusk shows the elevation of EY associated with a BZ enhancement, and the elevation at the dawn is associated with a relatively faster plasma flow. So the key point here is that we do have significant asymmetries during storms, and especially main phase. Just for the record, a similar plot can be made if you subtract the recovery phase statistics from the quiet time. It's just that with the main phase, it's more easy to see. That's why I kept that one as a main figure. And yes, the main point is that the plasma set indeed changes in an asymmetric way during storm times. So those were the first findings we had regarding the elevation of EY and therefore magnetic flux transport and how it maps throughout the plasma set. And the next thing we wanted to do is now wanted to see how the mesoscale contribution can change this picture, or how it actually helps us understand it. And just here, one of the caveats I want to highlight, while we do have a lot of points, and this is great because we can actually do statistics, this becomes a very big problem when we try to look at mesoscale structures. You can see, for example, here with geotail data that the sparsity we have, especially during the main phase, during bursty bulk flows, is extremely high. My takeaway, which is not the most positive one, I know, but at least I think it's something for us to remember, is that sometimes when we say the number of data points we have or events, it can be misleading, especially when we don't take into account the sparsity in the spatial domain, but also the actual driving conditions that we have for each of those events. Again, we can't do anything apart from waiting our satellites to gather more data or send more things up there. But it's good to remember that as a caveat in terms of our statistics. Still, we can do certain things with those data. The first thing we have to do is understand what we mean by mesoscale structure and burst intervals. Now, there have been many different definitions in the literature. Here, I took the same event from MMS, and I plotted it based on different definition I found through the literature. At the third panel, you have the typical one, which is what we used, with a fast flow being perpendicular to the magnetic field. Therefore, it has a magnetic flux transport associated to it. Then there are definitions that only use the bulk flow Vx component, others that discuss the depolarization aspect of that flow, and others that look exclusively on the convection electric field. Regardless of the criteria you use, you end up with a relatively similar data set, but again, with a few differences. But we can safely say that the broader speaking phenomena we look at is a 5-minute or a bit less interval of clear elevation in EY, BZ, and velocity that can be found in the plasmas. Now, I put here a lot of issues we have with the definitions and how we can actually do analysis. But again, I don't think it's the main point. My main point of listing those, apart from remembering them, is that because they are relatively rare, criteria can be arbitrary, and they are bursty, and we only have one spacecraft looking at one position, as we all know. We need to take a lot of assumptions into consideration before we do any statistics and any modeling that I will show you shortly. Still, we can do things, and we just have to be careful with what we're doing. So our work, which was led by our PhD student, Anushree Devanandan, was published this year, where we looked at the bursty bulk flows of geotail data, again, separating them in the same kind of approach between main recovery and quiet time. You can find the full paper through the QR code, but I wanted just to show you the key results of the work. So if we take all the BBFs and we do a superposed epoch analysis by lining them up here, which is the steepest point of velocity increase, as you can see from the top panel, we can actually get an image of the average behavior of a BBF as observed by geotail. What you can immediately see, if you look at A, B, and C, are again the same three quantities that we were looking before in the statistics. So you see that the velocity more or less reaches 200 kilometers per second. The magnetic field is clearly elevated before and after the BBF, which is a characteristic we found again for the storm time plasma sheet in general, and the EY is elevated. Interestingly, if we subtract the background here, I shaded it with red, so it's imagine that you just subtract this value out of all the examples that you have. You end up with a very interesting picture that shows that the velocity change with respect to the background is relatively similar between the different phases of the storm, and so is the depolarization aspect, which is roughly in the order of 1 to 2 nanotesla on average. It can be higher, of course, but you see that subtracting the actual elevation of the background field that we have in the plasma sheet makes the actual picture of BBF being relatively consistent, regardless of whether we'll have a storm or a non-storm interval. The next thing we did was that basically Anusri took all the events we had and showed that the difference in EY can be decomposed in different components, basically. So we have the difference in the velocity multiplied by the background field, the difference in velocity multiplied by the difference in field, and the background velocity multiplied by the difference in the field. Then we also have the cross terms between the z component of the velocity and the x of the magnetic field, but those are extremely small, and therefore they were not really necessary to be plotted. So you end up with this simple equation, and I think the main takeaway here is that the contribution from the delta Vx and Bz is by far the highest compared to the other terms. Or in other words, it is the enhancement of the velocity of the bursty bulk flow phenomenon on top of the already elevated magnetic field in the whole plasma sheet during the main phase of the storm that contributes the most for the elevation of the convection electric field. And again, in both storms and non-storm times, it seems like it is more the actual fast flow aspect rather than the polarization aspect that drives the elevated convection electric field during those phenomena. Another thing we tried to do was basically now take all these data that we had and try to look at different dawn and dusk asymmetries. This was kind of made to compare with the list of magnetotail reconnection that Nagai et al. Had in their paper. And what you can see here is basically if we take on the left the magnetic reconnection examples and we split them in different categories, there seems to be a downside preference when we are at the main phase of a storm. Similarly, if we do the same with the bursty bulk flow list from Anusri's paper at the beginning of this year, we get a similar downside preference for the main phase, which is shown with red here, and a dusk preference for the others. Don't take those kind of values too seriously because this is an ongoing effort. And again, as you saw from the sparsity of the bursty bulk flows and the reconnection, these kind of statistics can be prone to error. So right now we're in the process of combining MMS and Themis statistics to hopefully get a more coherent picture and increase the robustness of this result. So that's what I had for the first part. Basically, just to summarize the key points, what we found by doing all these statistics with storm time is that the plasma CTY is elevated, and this elevation seems to be associated with an increased background BZ. This enhancement in the equatorial magnetic field seems to be more prominent at the dusk side, while velocity is more elevated at the dawn. Now, when we looked at the storm time bursty bulk flows, it seemed like they are transporting more magnetic flux, but this enhancement is associated with a stronger background magnetic field, while the bursty bulk flow velocity is relatively constant. Also, an ongoing effort we are doing at the moment is to investigate whether a dawn-dusk asymmetry on BBF occurs and how this may be connected to a magnetic reconnection location and potentially to the dawn-side current wedge, which has drawn a lot of attention from the community. So you can find those two papers over here. And I mean, I can always take questions now, or we can move to the next part, depending on how you prefer to do this seminar. It's up to you.
We can take quick questions now if anyone has any. Okay, we'll save them for the end then. Go for it.
So the next step, after we did all this kind of more traditional analysis, is to do something more than that. And of course, when you have a lot of data, the easy answer is to just use machine learning and try to do some, as I called in the title, data-driven modeling. This is kind of the third part of the work. And our main question here was whether we can use solar wind information plus any ground magnetometers like we have from the indices in order to model the plasma sheet properties. Now, of course, there are many models out there that can do that. We'll discuss a few of them. And our main goal here was to see how well we can do during storm time and how well we can do with quiet time and compare and find the differences between the two. So what we are going to do is to basically compare with what baseline empirical models we have available. Historically, we have two different models that are typically used. One is the Tsigarenko-Mukai model from 2003. This was a model made with geotail data, and you can see here with synthetic input how it shows the density value throughout the plasma state region. And there is also the Dubagin 2016 model, which shows properties like the electron temperature here, and this was done by using Themis observations. Now, one question somebody would ask is, okay, since those are there, why are you doing this? And there are multiple answers to this question. I would say the most honest one is that there was not an MMS available dataset at that point, and we have quite some great instrumentation on board. Plus, a lot of those models are kind of stationary in the sense that they don't include time history. And we know that the magnetotail and magnetosphere in general is a model that has a memory, and it is driven on different scales. So if you do not include the history of the solar wind in the past, it is very likely that during certain periods like storms, you may end up with a not so accurate representation of the tail. So in those slides that I have following up, I'm showing what we managed to do with the modeling of the ion to electron temperature ratio and on the plasma density. We also have more things we can do, such as just the temperature or like explicitly the ion temperature of the electron and any other kind of plasma moment we have available on its mission. So again, just as a schematic, we take input from the solar wind. Explicitly here, we try to use information from L1, and we also take geomagnetic indices from the Earth, and our output is any kind of in situ properties from MMS and geotail. Themis can be, of course, used in the same way, but at least in our example here, we use it as a test rather than something in the modeling procedure. So with that in mind, let's see what we have. This I will skip. It's the same exact data set I showed you in the previous slides. All of those are originating from the very first work we did a couple of years ago, where we split the data set into different regimes. So this is looking at all the points of geotail and MMS mission in two different planes. So before I show you the results, since I'm very happy to have time to talk about this. Usually, with a shorter presentation, you never have time, but I think that it's very important to mention. I want to talk briefly about the different metrics that we use when we try to do those kind of models and how we are able to determine whether they are working or not. And this is just an example where if we take an interesting physical model, we may end up with certain metrics such as correlation that you see over here being relatively high. Of course, this is very important because it means that it captures the overall trend. But this doesn't necessarily mean that this is a model that actually captures the variability or the variation. For example, if you compare how this toy model I made on the left competes versus just an average value, you see that the rest of the metrics are kind of almost the same. The mean absolute error is equivalent, and the R squared is essentially zero in both cases. That means that while certain models can be useful in terms of understanding the physics, in terms of predictability or like predictive power, they can be very limited. And this can be very easily achieved if we average our data. Again, I'm not saying this is a bad thing to do because it can be very useful. But what it does a lot of time is that it creates an illusion because it shows that the underlying process is structured. For example, that density increases as we go closer to the Earth, but the actual local variation is hidden by either averaging our data or by basically sampling in space and time together by binning. So with those disclaimers, let's try to see what we managed to do in terms of results. And of course, again, as a reminder, when we put any kind of optimization algorithm like neural networks, machine learning, linear regression, you call it, we are essentially extrapolating, right? So this can be correct in a sense, as it can show meaningful agreement with observations, but it can also just be plain wrong. And we need to make sure that we differentiate between the two. So for our methodology, we did a couple of different things. We started with using a simple neural network, which is the panel B. Essentially, what you see on the left is the input time series from OmniWeb. It shows that our input was basically the velocity, the density, temperature, magnetic field, CMH, and AE indices, along with the location of the spacecraft that we're actually mapping in the plasmas. Then we use different algorithms, specifically neural networks, gradient boosting, and linear regression. And our output was basically either MMS or geotail and the different quantities that you see over here. On top of that, we used a very, very nice model that Conor O'Brien made, where basically it has those gated recurrent units. And rather than taking propagated to the Earth solar wind, it takes the actual input from wind spacecraft at L1 and takes into account any propagation error from the location of L1 to the Earth. This is very nice because basically, due to this and the fact that it can be trained with a distribution rather than a specific output, it has an embedded uncertainty quantification. So your output is not an actual value, but it's rather a mean and a standard deviation at that location, which allows, as we will see later, to create basically based on the sigma value, an uncertainty of your output and see how well it performs. Now, another takeaway from this slide is that we quantified our methods with many different variations in order to make sure that it was not the method or the data set or the time history that was driving the result, but it was basically a general finding, as we will see. So here is one of the standard plots the machine learning community is used to, which basically in the y-axis shows the prediction, and in the x-axis it shows the true value measured by the spacecraft. You can see on the first column that this is the gradient boosting algorithm. In the second one is the linear regression. Third is the Tsigarenko-Mukai empirical model. And on the right, we have the prime model that I just explained in the previous slide. Essentially, the closer we are to the x equals to y line, the better, because it means that the true value and the predicted value are closer to each other. So what we can immediately see here, without diving way too much into the what its point shows, is that the prime model and the gradient boosting work pretty well, while the linear models, which is the linear regression and Tsigarenko-Mukai, seem to be underperforming by having a very clear offset between the prediction and the true value that is measured. And this can also be found in the actual values. So if we write again the mean absolute error, the squared, the R squared skill score, and the correlation, you can see that especially prime, the plasma sheet model seems to outperform all the rest. And again, This advantage, I have to be super honest, it can get low. So this is more of a high-end advantage that I'm showing here. So depending on how you split the data, this kind of edge can be lower, but it's always there. And we will see why this is the case, that regardless of the model and how complicated it becomes, you cannot really exceed a specific performance. But since prime PS performs the best out of the methods, the rest of the plots are basically assuming that this is the optimal algorithmic solution, at least. So after we determine that with the actual data, we can do a good job at reproducing them, the next question is, what can we do to model different conditions in the plasma set? And that's basically what we try to do in a similar fashion like the Tsingarenko-Mukai model did and others in the past. And here you can see a comparison between the two different efforts. On the right, it's the empirical modeling from Tsingarenko-Mukai, which, as you can see, is a symmetric model. Therefore, whether you're at the dawn or the dusk, it creates basically the same picture. And you can see on its subtitle what are the driving conditions. To explain this a bit more, what we do here is that we drive the model with constant conditions, and we only vary the BZ component of the solar wind and the actual density. What you can see here is that with our model, we were able to generate asymmetries by having a higher plasma seed density found at the dawn, which seems to be always the case. Plus, when we have a northward magnetic field in the solar wind and the higher solar wind density, the overall density seems to increase uniformly throughout the plasma seed region. We can do the same experiment now by looking at a more complex quantity, such as the temperature ratio between ions and electrons. What we see here is that basically with our approach, we get relatively less spikes, less high values, and we also generate asymmetries that are expected from the literature. For example, that at the dusk side, there is an increase in the ion to electron temperature ratio, and also during higher velocity, during higher velocities, we also get higher I think this is wrong actually. This is correct. We get higher Ti over T on the dusk. Then I have a few slides on some community reminders. I will not go into too much detail. I'm just going to say here that one of the things we need to remember is that the temperature is a very hard moment to calculate, and whether it is meaningful or not, if the distribution is not Maxwellian, is a discussion to be made. But my main point is that, at least observationally, in order to be sure that the temperature is correctly accurate, some post-process might be needed. You see a great example here made by Tien Vo, which I asked him to, through his algorithm, which is openly available, by the way, so it's easy to find on GitHub. I forgot to put a link here. But you can remove the ion penetrating radiation coming from SEPs, which can have a very drastic difference on the actual calculation of moments. What this slide really wants to say is that the ground truth can vary a lot depending on the process. So when we have a model being accurate, we need to remember what we are comparing it with. And just as an illustration, again, the same kind of note. Here you see a distribution of the Ti over T value from MMS, shown as orange for the full distribution, and as blue with what I call here partial distribution. Partial distribution essentially means that we only use specific energy bins to integrate that we know are not affected by things like penetrating radiation that I showed you in the previous slide. That means that we can be relatively more certain, again, not fully certain, that the blue distribution is more accurate or like closer to reality compared to the orange one. And here the main point is that this difference can be very drastic. It can be like 30%. So while I'm very happy when I have a model that is 30% more accurate, it is also a question to be made whether we want first to make our ground truth be 30% more close to reality before we do any modeling. I say I have a few more minutes, so I will also show those. Basically, what I want to highlight here is what we found when we compared our model during storm and quiet times. The problem we have during storms, as I said at the beginning, is that our strict thresholds can be very uh, may not work as we expect them to. In other words, sometimes during storms, because we have these very high pressure pulses in the solar wind, you end up with properties in the plasma sheet that the same thresholds we use may not capture those observations as plasma seed, but may mistaking them as something else. So long story short, apart from the typical plasma seed criteria we added an additional one called high density, which was basically manually picked high density intervals in the plasma seed during very strong storms that we knew geotail was in the tail. And we wanted to see what the effect is if we include those in the training compared to when we didn't include them in the training. And you can see the results over here. What you see plotted is basically the prime model in red when you include those high density intervals. And in blue, you can see the same model when you train it without those high density intervals. In black, you can see the observation of Themis during that time, which was in the plasma sheet region close to the Earth. And with green, you can see the Chicago-Munkai model plotted all in the same panel. B panel shows the difference between each of the model, red, blue, and green, with respect to the actual values of Themis. Just a note here, Themis observations that are dotted is just a temporary transition of Themis towards the lobes. As you may know, when you have a storm, there is a lot of flapping of the magnetotail. The actual spacecraft can be located in this plasma sheet and then in the lobes in a very rapid changes. Here, the main conclusion is that by including those high density intervals in the training set, we were able to increase the performance of our machine learning model much higher compared to what it was before. And you can see that also, visually on how well the red line is with respect to the black observations, but also through the statistics and absolute error and R square that are plotted in the list. Now, if we do the same for the same storm, the November 2023, we can compare how our model does on ion to electron temperature ratio with respect to observations. Now, as you can see, there is an overall good agreement. Values are between 3 and 7, and our model predicts roughly 4 and 7. Now, this is great, but one argument or one question that one may ask is how much better is this compared to a flat line at around 4? I would say that's a fair criticism, but I would say that's relatively boring. The thing is that it is very difficult to predict this, and arguably during this interval, it seems like the Ti over T can range quite rapidly, and our model works kind of okay around that. Now, the last thing I wanted to show is how we can actually get some kind of physical intuition on why our results perform the way they do, and what can we do in the future to make those better. What I show here is what in the machine learning community call feature analysis or sub values. Long story short, red means high, blue means low, and left and right basically says how important the input was. So essentially here we look at how important each of the input is to drive the density in our model. So you can translate the first line as, since it's blue here, it means that when we are far from the magnetotail, the density is lower. And since it's red here, it means that when we are closer to the magnetotail, to the Earth, the density is higher. Similarly, the dawn-dusk asymmetry can also be found in the Y component, since when we are at the dusk, when we are at the dawn, which is negative values for Y, density is higher, and similarly when we are at the dusk, density is lower. So what this tells us is that basically for the majority of the cases, the two dominant features is basically the location of the spacecraft. In other words, the solar wind input has a relatively lower effect to drive the model compared to the actual location. And this can also be found in this plot, where we basically merge the time history. So here you can see that on the left, what happens during quiet time. During quiet times, it seems like if we merge all the time history of our solar wind, basically you can almost get fully useful models by looking at the location of the spacecraft and how far it is from the Earth, BZ, density, and the location in Y. This is great because this is actually the dominant features used in models like Tsgener-Komukai in the past. So there is a very clear agreement and reproducibility on this. However, when we go to storms, we see that the actual model becomes much more driven. The feature that is most important is not anymore the location of the spacecraft, but it is the actual driver. This is, again, super important because it shows how those models can be useful in contrast to the ones that have a stationary weight, regardless whether you're in storm or non-storm behavior. Again, this is preliminary though, and I have to clarify that this type of analysis should take into account that a lot of those quantities are intercorrelated. For example, we do know that AE index and VEX, the velocity of the solar wind, can be correlated. Therefore, it is not trivial to disentangle those from each other and attribute how important they are for the model. So here I have the main takeaways included from the first part of the presentation and the machine learning one. I think I've already repeated quite a lot the first part, so I will focus on the machine learning one. What we essentially have on the machine learning is a model that outperforms previous empirical models and overall generates a physically accurate picture. Of course, though, the sparse conditions and the sparse data during those rare conditions can degrade the model performance. And one easy solution is to really go and handpick the data that we train with. But this is not a real solution. It's more of a band-aid just to fix it temporarily and do the best that we have. In reality, we need to find a more systematic approach on storm time modeling to solve this. And the last slide I have here is about the future steps, what we want to do. Essentially, what we have done already is look at all the geotail and MMS observations. What we hope, both for the actual physical analysis and for the modeling, is to include the latest MMS data from up to 2026, and also include Themis observations. There is, of course, a very big issue with that in terms of actual modeling, because every instrument is different, but at least in certain physical questions, like where BBFs happen, or whether there is a clear asymmetry in the properties, the different instruments can be used together, at least to a certain degree. Hopefully, we'll be able to do also similar modeling to understand substorm activity during quiet times, which is more relevant to the cinema mission, and also potentially get a functional model that can be used for more complex physical properties, such as, for example, the non-Maxwellianity parameter, or the kappa, if you fit a distribution to it, or things like magnetic curvature, as it was done statistically for the MMS one. So that's all I have for today, and I'm open to any questions.
Thank you so much, Savvas, for a wonderful talk. We can start taking any questions. Feel free to either raise your hand or unmute yourself, or put comments in the chat. We can read those from there. Robin, why don't you go for it?
Yeah, it's just a comment and a question. It's not really our primary data product, but we will have the capability with Cinema to produce a temperature and pressure data product, which will be kind of similar to the maps that you see with DMSP data. But of course, we have more spacecraft and also better coverage on the night side. And so, Tom, maybe you can, I can't remember if we will get maps over a course of a day or something like that. Is that right? I don't know, Tom.
Yes.
Okay.
I mean, we'll have regional maps over the local times that we cover.
Right, we have 15 orbits per day, and over that
Yes,
in orbit, we walk in magnetic local time from dawn to dusk.
right, so every half day, we'll cover as much as we can cover, which will be most of the tail.
So that will be an interesting, different perspective from the in situ measurements. And then maybe a question is, how do you interpret the result that the location feature is more important than the solar wind driving, at least for non-storm times? Or do you have any sense for why that, or would it make sense to look at kind of a deviation from an average plasma sheet then or something?
Yes, this is a great question. We've been thinking about that for quite some time. So I think that the easy answer to the first part of the question is that most of the times the plasma set is super boring. In a sense, there is super boring as in very predictable. The location can dictate the average value throughout the whole region, and that's why things like density seems to be mostly dictated by that. Now, what we tried before was to kind of do exactly as you said, like take an empirical model like Tsikarenko-Mukai, subtract it, and then try to predict the deviation of that. That worked quite well, and it did produce different features. So this whole thing will be very different. Location didn't matter anymore because you basically have subtracted it. So that's a good way to get physical insight. Sadly, though, in terms of total performance, like how accurate was our deviation model on top of Tsigarenko-Mukai versus how accurate is the model that we have now, it was very similar. So in terms of prediction, it didn't make a big difference. But it can be definitely used to get more physical information, as in which driving condition plays the most important role.
Okay, thanks. And I think there's a question in the chat too.
Yeah, Habaturkigan is asking you kind of how are you defining your quiet time periods? Are you requiring kind of a period of very limited SMR ahead of that? Or I guess how are you sure that your quiet times are not being affected by lingering storm time effects?
Yes, let me try to go back. I'll have to remember a bit. I have to admit it's been a while, but so what we basically did was that we required that a storm has to have a minus 50 nanotesla. So any storm or like any kind of depletion of SMR less than that was kind of embedded within what we call a quiet time. This is, of course, a caveat. And again, I'm pretty sure this is discussed more strongly in this recently published paper. And to make sure that we didn't have any kind of lingering storm, we required that the storm period would end when we reach minus 20 nanotesla. So when we registered a storm, it had to kind of recover up to minus 20 nanotesla, and then anything beyond that would have been quiet time. So in that way, we were kind of more sure about that. And there is also a more pragmatic answer to your question that storms are a very rare phenomenon. So as you can see here from the percentages, in reality, it is roughly 10 to 12%. Even so, while the quiet time was like 90%. That means that statistically, even if we had a couple of lingering intervals from a misclassification of a storm, they wouldn't affect the quiet time. It's more the opposite that might create a problem that we are missing storms rather than storms affecting the quiet time. I don't know if that helped.
Yeah. Thanks, Alice. Andre has a question.
Yeah. Hey, Savvas, thank you very much. Very interesting presentation. I have a question on your first part of your talk. When you compared, I guess it was the convolution of flux transport, and you said that velocity is the main contributor. Is it correct?
Do you mean for the Bursty bulk flows here?
Yes, I think it's here. So the maybe couple of slides or not, yeah. So your point here is that essentially the velocity, the flux, better say, a second moment of distribution is the main contributor. I just wonder if doesn't it, uh, depend on where you are in the system. I can easily think on, say transition region when the electric transport is is less than the transport due to energy dependent drifts. Will it be valid there?
Yes, Andre, you're absolutely right. What really shows in this plot is what the average PBF observed by geotail has to tell us. So this is heavily affected by the fact, as I showed in this plot, that most, if not all, of the geotail observations are further to the tail from 20 RE. That means that indeed this picture is not valid anymore if we go closer to the transition region and overall closer to the Earth. So maybe doing a very similar analysis with Themis observations, which are closer, and compare would be a nice step forward to see what you already implied. I think, if I understood correctly, that probably the velocity terms has a relatively lower contribution compared to the other.
Yeah, you may compare, for example, with Christine statistics. It was 2014 or 2013. Christine, correct me if I'm wrong. That showed basically that dipolarization, BZ, is the main factor.
Yeah, that's a great point. I need to look into that and see how to compare, but at least intuitively, it seems like what you describe is the case, that the closer we are, the relative importance should shift.
All right, thank you.
Thank you.
Awesome. Any other questions for Savvas? I just had a really quick one. When you were showing the ion to electron temperature ratio combining the empirical models of Sengineko and Boygan, there was I think heightened ratio on the Don side, although the empirical model was saturated the color bar. Do you know, I guess, what's the cause of that feature and
Yes,
why is
so
it so much different than your predicted model?
yeah, so I have to admit, I always feel bad about showing this picture on the right, mostly because I am kind of not being fair to the model, to the empirical one. If I go back to this picture, you see that the empirical model is basically defined much closer to the Earth. So what really happens here is that because we force it to go kind of outside its trained regime, you get very high values for very low values for the electron temperature, and as a result, it saturates when you compare TI over TE. So to be fair, those values fall outside of the DSGR model, and therefore they are not to be trusted. So it's not a caveat of their model. It's more of that a model doesn't exist in that regime, while the one we train with MMS seems to produce at least reasonable values with the same physical picture.
Thank you. Any final questions for Savvas? If not, let's thank our speaker again for another wonderful talk. Appreciate you giving this to us. I wanted to, before I let everyone go, I wanted to let you know that we will have our next community Cinema Community Science meeting in 5 weeks, this time on June 25th. John Dorelli will be giving a talk on the night side science opportunities with the Tracers mission and how we can kind of combine those with cinema moving forward, which should be extremely interesting talk. And then we'll take a little bit of a break for the summer, since I know a lot of people will be attending conferences and so forth. So thank you again, Savvas, for a wonderful presentation. I hope to see all of you in at the end of June.
Thank you. Bye.
I
Bye.